In Module 5, we're going to start a new topic, and that topic is load strength interference. In many ways, this topic is fundamental to this course. In other words, how to affect engineering design to achieve the reliability that we seek. So, in many ways, load strength interference is a core concept of how to design so as to achieve a specified reliability. So we know that failures occur when load exceeds strength of the material, and in our case we might refer to as load to mechanical stress or any quantity that is imposed and that is resisted by some material property that we will call as strength. So for instance, in addition to mechanical stress, voltage could be a load. Temperature could also be a load. It could be a thermal load. Most electronics basically experience thermal cycles, and that cause them to fail. And strength is any resisting physical property, such as mechanical strength or melting point, etc. So in traditional design, the designer considers the extreme values of load and strength. So in other words, we take the extreme load to design conservatively. And we also lump all that we don't lump our uncertainty about material property, etc., through a safety factor. So we basically use a safety factor to ensure that the load, the stress, for instance, will not exceed some allowable stress, which is strength, nominal strength. Okay, nominal, because it may not be the real. It's nominal strength divided by some safety factor. So the allowable stress is nominal strength divided by a safety factor, and we ensure that the load is always lower than the stress is always lower than the allowable stress. So there's a lot of uncertainty that gets lumped into the safety factor. The uncertainty gets lumped into the safety factor. And sometimes we put in a larger safety factor when the impact of failure is serious, such as in a pressure vessel. If it explodes, it might have some catastrophic consequence to human lives, and therefore we put a larger safety factor. So this safety factor accounts for all of our uncertainty associated with the design. And again, if you recall from our earlier discussion, the uncertainty comes about because of uncertainty in geometry or load history or material behavior. So we'll lump all of that into one safety factor. So let's look at safety factors that are common for many applications. So here, for instance, if you take machinery, most of the time the machinery is made of steel. Okay, and the safety factors that we use are typically 1.5 to 2. So machinery 1.5 to 2. If you take pressure vessels, carbon steel, safety factor is much higher because the risk, if the pressure vessel were to fracture, the risk to human life is significantly higher. So we want to design the pressure vessel to much more conservatively with safety factors of 5. And if the same pressure vessel were to be designed with cast iron, were to be made with cast iron, we would use even higher safety factor. And the reason for that is because we have less confidence in our understanding of strength of cast iron. There's more variability. And therefore, we would use a much higher safety factor. If it is alloy steels, we might use a slightly lower safety factor because we have greater confidence in the strength of alloy steel, and similarly non-ferrous materials. Airplanes, The safety factor typically is around 1.5 against ultimate, 1 against yield. And the reason why we would want to go with lower safety factor is because a conservative design would be a very heavy aircraft that's not suitable, and therefore we need to reduce the factor of safety, and the only way you can do that is by extensive testing. So any improvement in factor of safety has to come, any lowering of factor of safety has to come with extensive testing. And because of the risk to human lives, we were willing to do that level of extensive testing for airplanes. Bridges, if it is structural metals and reinforced concrete, its factor of safety around 2. If you have wooden bridge, the factor of safety is 6, again because we have less confidence in our understanding of the failure of wood, the strength of wood. It has more variability with grain orientation, etc. Buildings, again, 1.7 to 1.8. And again, if you go with a material that we don't understand as well, or it varies quite a bit, the strength varies quite a bit, then you will put a larger factor of safety. So allowable working stress is strength divided by factor of safety. Okay, as we discussed, and that's how we design traditionally. What we will do in this course is to try to develop a better understanding of load and strength and identify the population that is at risk. So we'll assume that the load and strength are statistically distributed as they are, and failure will occur if the distributions overlap. So in other words, if the strength curve overlaps with the load curve, there is population in this region here, in this interference region, that is at risk of failure, where the strength will be lower than the applied load. So what we want to do is to estimate this population and specify this population in designing a product. So in order to do that, we need to have an understanding of load distribution, the probabilistic distribution of the load, and the probabilistic distribution of the strength. Now, in order to carry out the design using this load strength interference concept, we will define two quantities, statistical quantities, two factors, if you will. And those factors are what are called safety margin and load roughness. Safety margin is defined as this y here corresponds to strength. So the safety margin is the mean value of strength minus the mean value of load. L here corresponds to the load. Again, these are generic. Okay, divided by squared standard deviation of strength plus squared standard deviation of load, whole thing raised to the power 1/2. And we will derive this formula using our understanding of expectation and variance. So this actually corresponds to, the denominator actually corresponds to the standard deviation of y minus L. That's what this denominator corresponds to. So we'll derive this formally in the next module, module 5.2. And the second parameter that we will use for probabilistic design is the load roughness. And load roughness is defined as standard deviation of load divided by standard deviation of y minus L. Okay, remember, if y and L are independent, the variance of y minus L is variance of y plus the variance of L. So this actually is the standard deviation corresponding to raised to the power 1/2 gives you the standard deviation corresponding to difference between y and L. We'll do this more formally in module 5.2. So in doing probabilistic design, we're going to use these two factors: safety margin, which is defined this way, and load roughness, which is defined this way. So we can either specify load roughness, we will most often specify load roughness, acceptable load roughness, and then we will specify safety margin, which is our desired reliability. So this is our desired, this represents our desired reliability somehow. We will see how in the next module. And this defines our desired load spread, and then we will go about identifying part dimensions that meet our desired reliability and desired load roughness. So in words, safety margin is the relative separation of the mean values of load and strength, and loading roughness is the standard deviation of the load normalized. Both of them are normalized by the standard deviation of load strength minus load. Let's look at some scenarios. So case 1, you have a high safety margin and low load roughness. Low load roughness means that the distribution of load is fairly narrow. The standard deviation of load is fairly small compared to standard deviation of strength. Okay, that's what the load roughness means. So if I have low load roughness and high safety margin, the design is intrinsically safe. And case 2, you have low safety margin. The separation between strength and load is small, and you also have low load roughness. So this is a possibility as well. The reason why you have low safety margin is because strength is distributed much more, which is typical for most materials. So strength tends to be fairly widely distributed. So during a design phase, you have to distinguish between design phase and use phase. During design phase, when you've chosen for a given material, there's usually a wide variation in strength. So during design phase, you want to characterize the strength distribution quite carefully. And the load distribution is what you hope would be the user would use your product under. Okay, so for instance, if I'm Microsoft making tablets, Surface Pro tablets, I might have a certain specified use scenario where I might allow it to drop from 3 feet. But then once in a while, as I showed in the introduction video, there might come a user who doesn't drop it from 3 feet but throws it into a stance. So this is what we anticipate during design phase, and this is the strength distribution is what we would like to characterize during design phase. So we have a clear understanding of at-risk population that we will accept and say, okay, I'm willing to live with X number of my parts failing. So here, instead of specifying a factor of safety which lumps all of this into some factor of safety, all of this uncertainty into a factor of safety, here we take extra effort to characterize the strength distribution that allows us to specify precisely the population at risk. Now, the first case was high safety margin, low load roughness, intrinsically safe. Second case, there is low safety margin, low load roughness, and that's because of a large distribution of strength, and there is a small population that is at risk. And the third possibility is you have a low safety margin but high load roughness. So you have a high load roughness. And this situation you hope to avoid by specifying acceptable load roughness, but then you cannot prevent users from abusing a product. So this might happen as well. So the user might decide to test the limit of your product by subjecting it to a load roughness much greater than what you were willing to accept. So here you might have a larger fraction of the population susceptible to extreme load events. So you hope to avoid this by specifying a use environment, but you can't control it. So this is the third possibility. Now, having described these three possibilities, I must also mention something that is commonly done in industrial practice, and that is screening. So let's say I have an at-risk population. Is there some way I can eliminate at-risk population before I send the product out to the field? And that is through something we call a screening. So let's say I have a load and strength distributions as shown here. And there is an overlapping region here where there is at-risk population. So what I might want to do is to somehow eliminate that population in the hope that I don't have any overlap between load and strength. The way I might do that is by applying a larger load than I expect the user will subject the product to. So this is the larger load I subject the part to before I send it out to the field. After manufacture, I subject it to some larger load. And as a result, I take out some population and I make sure that this larger load is not so large as to weaken the whole population, but only a small portion of the population is weakened. And some of them will fail, or many of them will fail. And then as a result of that, what I've done now is to increase the safety margin, because I've now eliminated that population that was potentially susceptible to load strength interference by applying a larger load. So this is screening. So screening is equivalent to truncating the strength curve. So those are the basic concepts of load strength interference. And that concludes module 5.1. But in module 5.2, I will analyze mathematically load strength interference.